D.
The reaction rate of a chemical reaction describes how quickly or how slowly a chemical reaction takes place. We're going to make some assumptions in this tutorial just to simplify our math. These are the same assumptions that would be made in any first year chemistry course. So we are only going to be looking at examples of a single chemical reaction that's occurring under closed conditions in a constant volume and without a significant buildup of reaction intermediates. We also want to remember that our reaction rate can really be expressed in terms of how quickly your reactant is disappearing or how quickly your product is appearing. So you can describe the overall rate of a chemical reaction by looking at either one of your reactants or one of your products. And we are going to define rate as a change in the concentration of either our reactant or product over the change in time. So let's just look at one example here where we're going to calculate an average reaction rate. So we're going to use the data in the table below and calculate the average rate of the appearance of a product, we'll just call that product C, over the time interval from 10 seconds to 20 seconds. So in this problem, we have our graph and we have time on the top, and then we have the concentration of product C, which is given to us in molarity. So in order to calculate the rate for this reaction, we're going to look at the change in the concentration of C over the change in time. Remember that your delta symbol means change in. And so we're going to look at our final concentration of product C minus our initial concentration of product C to give us the change in the concentration of product C over our final time minus our initial time. So this is the section of the graph that we're focusing on because we are looking to calculate the average rate from 10 to 20 seconds. So we are going to call 20 seconds our final time and 10 seconds our initial time, which means that our final concentration of C is going to be 1 molar. So there's our final concentration of C minus our initial concentration of C, which is going to be 0.7 molar. So that will give us a change in the concentration of product C over the change in time. So our final time minus our initial time, which is what we put down here on the bottom. And we'll get that the concentration of C changed by 0.3 molar over a time interval of 10 seconds. And then you can just divide those two numbers and you'll get an average rate of 0.03 molar per second. And so when you're calculating the average reaction rate, you could calculate it over any time period. We could have calculated the average reaction rate for this reaction from, let's say, a period of 5 seconds to 20 seconds. We would get an answer that's a little bit different. Or if we went from 0 seconds to 25 seconds, we'd get an answer that's probably even a little bit different still. So one of the things that you're going to notice if you study reaction rates is that they are going to change over time as your reactants are being used up. Generally, your reactions are going to slow down over time. So when we calculate the average rate, we do really need to be specific about the time frame that we're calculating that average reaction rate for. Okay, let's talk a little bit now about reaction rates and stoichiometry. So we said at the beginning of this tutorial that you can express a reaction rate in terms of either appearance of a product, and that's what we just did, or in terms of disappearance of a reactant. Remember that the coefficients in your balanced chemical equation represent the relative number of moles of the respective reactants and products in a chemical reaction. And so this goes back to stoichiometry, and I have additional tutorials on this and mole ratios, but these coefficients are going to give us relative amounts of our reactants and our products. So just to kind of refresh your memory here, what this balanced reaction is telling us is it's telling us for every 2 moles of H2O that would get used up, we're going to make 2 moles of H2, and we're also going to make 1 mole of O2. So you could see also from this balanced equation that the rate of the disappearance of H2O is going to be equal to the rate of the appearance of H2 because the coefficients are the same there. You might also notice, and we'll talk about this more specifically as we go through this, But you might also notice that you are going to use up H2O faster than you're going to make O2 as a product. So you're going to use up 2 moles of water or 2 molecules of water for every 1 mole of oxygen or molecule of oxygen that you make. Okay, so you can use dimensional analysis to look at relative rates of reactants disappearing and products appearing, but I'm just going to give you a general chemical reaction here and show you how the rates of either the disappearance of the reactants or the appearance of the products are related to each other. And so this is just a balanced chemical reaction where the lowercase letters represent my coefficients. This kind of notation down here at the bottom is just going to tell you how the rates are related to each other. The other thing that I want to point out here is that when we look at the rates, notice I put a negative sign here and a negative sign here for reactant Q and reactant R. That's because we're looking at the disappearance of these reactants, but our rates are always going to be positive numbers. We're always looking at the change in. So this is just kind of convention here to put this negative sign here just to give us a positive value for a rate. Okay, so if you take 1 over the coefficient of a reactant or product and you multiply it by the rate of change of that reactant or product, you can relate that to the disappearance of any other reactant or the appearance of any other product. And so this kind of looks like a lot of letters here. I'm going to show you what I mean in the next here. So let's look at this problem here. This says if the rate of appearance of ammonia, which is NH3, at a given instant in time is 5.7 times 10 to the negative third molar per second, what is the rate of the disappearance of hydrogen? So let's just look at this qualitatively here for a second, and then I'll show you the math involved. So we're looking at the rate of appearance of ammonia and the rate of the disappearance of hydrogen. What you can see just from this is that we're going to need 3 H2 molecules for every 2 molecules of NH3 that we're going to make. So qualitatively speaking, if I know the rate of appearance of ammonia is 5.7 times 10 to the negative third molar per second, I'm going to predict that the rate of the disappearance of hydrogen is going to be a larger value than that because I know I'm using up hydrogen more quickly than I'm making ammonia. So let's go ahead and do the math and see if this checks out. So I know that these rates are related to each other via this equation here. So I should have a negative sign here if I really want to be correct. That's just telling me that the H2 is disappearing. Again, that's what we use the positive and negative signs for here when we're talking about rate. But generally, when we report rates, we just talk about rates in absolute value terms. Okay, so I know that the rate of the disappearance of hydrogen is related to the rate of the appearance of ammonia. So here's my rate of the disappearance of hydrogen multiplied by the inverse of its coefficient. I know that's going to be equal to the rate of the appearance of ammonia multiplied by the inverse of its coefficient. One of the things I want to point out here that students tend to struggle with, and I erased all my writing so that you can see this, is that the coefficients just tell us how the rate of the disappearance of, say, one reactant relates to the rate of the appearance of a product or the disappearance of another reactant. And so we use the inverse of those coefficients to give us relative numbers here. But I want to point out that this, what I've highlighted in blue here, the change in the concentration of H2 over the change in time, this is the rate of the disappearance of hydrogen. And so this is the term I'm solving for in this equation. And so when you look at this equation, you need to not forget that. So what that means is that if I were to take 1/3 times the rate of the disappearance of hydrogen, that should be equal to 1/2 times the rate of the appearance of ammonia. And so don't just lump this fraction in here with our actual rates. Okay, so when we look at information that we're given in the problem says if the rate of appearance of ammonia at a given instant in time is 5.7 times 10 to the negative third molar per second, that is what we are going to plug in here. That is referring to this term right here. This is the rate of the disappearance of ammonia. And so that's what I'm talking about when I say this number. So if I take this rate of the appearance of ammonia and I multiply it by 1/2, and then I solve for the rate of the disappearance of hydrogen by dividing each side by 1/3, you get an equation that is going to look like this. So the rate of H2 disappearance, and let's just write that again like this. All I did is I'm just solving for this term here, is going to be equal to 3/2 times, this is the rate of the appearance of ammonia. So I just consolidated everything to one side to get this term that I'm trying to solve for alone. So this is just our simple algebra here. And then when I plug in here the rate of the appearance of ammonia and multiply it by 3/2, I will get that the rate of the disappearance of H2 is 8.6 times 10 to the negative third molar per second. And this checks out with what we originally suspected we would find. We suspected that we would find that H2 is going to disappear faster than NH3 is made, because you're going to need 3 molecules of H2 to make 2 molecules of NH3. And that's what we get. We get a number that is larger than the rate of the appearance of ammonia.